Okay, so we're going to pick up from yesterday with tangential velocity. I have this diagram here of this odd bicycle, big front wheel, small back wheel. Now let's look at 2 points on this bicycle wheel. So let's look at a point right here and then a point right here. Now if this bicycle is in motion, these 2 points will have the same angular velocity. So yesterday we talked about angular velocity. So let's just say that this outer point right here is moving around with an angular velocity of 1 revolution per second. If this outer point moves around at 1 revolution per second, what must be the angular velocity of the inner point? Also 1 revolution per second. Does that make sense? So 2 points orbiting the same center, such as this bicycle wheel here, will travel around with equal angular velocities. Now, tangential velocity. Where do we get the term tangential from? Well, from the word tangent. So the best way to think about tangential velocity, and tangential velocity is measured in meters per second. It's a linear velocity. This is measured in meters per second. The best way to wrap your brain around it is imagine a little pebble jammed into this wheel and the bicycle's in motion. If a little pebble were right here and it flew off the bicycle wheel as the bicycle wheel is in motion, how would the little pebble leave the circular path? Tangent to the circle. What if the little pebble were over here? How would it leave the circle right there? Tangent to the circular path. That make sense? Now, this inner point here. So this inner point is also moving around in a circle. So say you had a little tiny pebble that was jammed into your bicycle spokes. If there were a little pebble there and the bicycle were in motion and then the pebble broke free and flew off, how would that little pebble leave the circular path? Tangent to the circular path. Now look, would these 2 tangential velocities be equal? No. The angular velocities were equal. You see, angular velocity is revolutions per second, degrees per second, radians per second. Those are the 3 possible units. But tangential velocity, it's a linear velocity measured in meters per second. So which point is traveling faster in the linear sense, in the tangential sense? Which of these 2 points is going to have a larger tangential velocity? The outer one. And it makes sense because look, the outer one has a farther distance to travel in the same time as the smaller circle, right? The outer point is covering a farther distance in the same time that the inner point covers a shorter distance. Does that make sense? Okay, so let's talk about this equation. Now look, I would add this to the Spaldo notes. For probably like the last 3 years, I've been like, oh, Spaldo, you got to add this equation. It's still not in my typed up Spaldo notes because I keep forgetting to add it, so I would write that in. But look, where does this equation come from? It's basically velocity equals distance over time, where you're focusing on 1 complete circle. What's the distance around 1 complete circle? The distance around 1 complete circle is 2 pi r. That's the circumference. And then there's a special name for the time for 1 circle. That is what? Period. So capital T is period. We talked about that yesterday. What's the definition of period? The time for 1 cycle. There's 4 different things in physics that you're going to have to know the periods for. So 1 period is the time for 1 circle. Number 2, period could be the time for a complete cycle for a pendulum. A pendulum going there back. The time for 1 complete there back is the period. Third one is mass on a spring. A mass going doing, doing, right? If you have a mass bouncing up and down on a spring, the period would be the time for 1 complete cycle. The last one is, who remembers? Waves. The period of a wave is the time for one complete wave. Okay. All right. Now this equation right here, tangential velocity. Another way to get it is you take the angular velocity and multiply by r, where r is the distance from the center. It's the radius. So notice that as r gets bigger, as the radius gets bigger, the tangential velocity gets bigger. This angular velocity here has to be radians per second. You have to be in radians when you're using that equation. Okay? All right. I picked this bicycle wheel on purpose because we have a big front wheel and a small back wheel. So something to be aware of is this. If this bicycle were in motion, and let's say that the whole bicycle had some velocity v, like the bicycle as a whole, it's cruising down the road. The bicycle as a whole has a velocity v. Well, that velocity v is going to be equal to the tangential velocity of a point on the wheel, on the edge of the wheel, big wheel or small wheel, right? So see, a point on the perimeter of the big wheel has a tangential velocity. A point on the perimeter of the small wheel has a tangential velocity. All three of these velocities would be equal. Does that make sense? All three of those velocities are equal. The velocity of a point on the perimeter of the wheel, the tangential velocity, is the same as the velocity of the object. Okay? Now, if you have a small wheel and a big wheel, which of those wheels is going to have a larger angular velocity? The small one. Because look, that velocity, the tangential velocities are equal. So apply this equation right here. So let's just say, V1 equals V2. Let's say that 1 is the small wheel, 2 is the big wheel. So plugging in for this is going to be angular velocity 1 times radius 1 equals angular velocity 2 times radius 2. So look, the small wheel has a small radius. I'm going to put an arrow pointing down, meaning the radius is small, which means what has to be true for the angular velocity? Has to be big. And then for the big wheel, the radius is big, but the angular velocity is small. Okay? All right, moving on. Okay, the main event, the main thing for Chapter 7 is this: centripetal acceleration. Now, what I want you to do is get the idea out of your head that acceleration is always about faster, 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 and slower, slower, slower. In this chapter, in Chapter 7, here is your acceleration. Here is your acceleration. Is this going faster, faster, faster? No. Is it going slower, slower, slower? No. So why is this accelerating? Because the direction is changing, right? An object in a circular path, the direction constantly changes. So here's the basic definition for acceleration, but you got to realize that velocity has two parts. It has magnitude and it has direction. If an object's going faster, 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 or slower, 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 that's a change of magnitude. That's what we did earlier in the year. We already did that acceleration. Now what we're talking about is what about a change of velocity because the direction changes? Well, that's referred to as a centripetal acceleration. The word centripetal means center seeking. Centripetal means center seeking. Now, why would we refer to it as center seeking? Well, look, centripetal acceleration, and I'm going to show you why. I'm going to give you a little vector proof. Centripetal acceleration always points to the center. It's always to the center of the circle. So here's a little explanation why, a little vector explanation. But to understand this explanation, you need to know that when you're adding vectors, so I have my two little arrows here for vectors. When you add vectors together, how do you add them? You place them together how? Tip to tail, and then the answer that you're looking for goes from the tail of the first to the tip of the last. That's how you add vectors. So Here we have a guy swinging this chunk of metal around. So let's say here's a diagram. We have this point right here represents the initial. This is the object at the initial point. And then a split second later, I'm talking like a millisecond later, the object's right there. So did the magnitude change? From here to there, did the magnitude change? Magnitude stayed the same. Did the direction change? Yes. If you do basic vector addition for these two vectors, you're going to see that the change of velocity is directly to the center. It's going to be directly to the center of the circle. All right, so look. Acceleration is change of velocity over time. Well, what's change of velocity? Change of velocity is v final minus v initial. Oh, let me change this to vi so it agrees. The diagrams are using vi for v initial. So v final minus v initial. So look, what is negative v initial? So look, if this is v initial right here, what's negative v initial? The same thing, but the other way, right? That'd be negative v initial, right? So if you look at this diagram over here, what was done in this diagram? We took v final and negative v initial, stuck them together how? Tip to tail. The resultant vector goes from the tail of the first to the tip of the last, so that's the resultant right there. That's the change of velocity. Notice which way that points. Which way does that point? Straight down to the center of the circle. So the whole point here, when an object's in a circular path, which way is the velocity changing towards? Towards the center. So then kids are like this. I've heard this 1,000 times. Well, if the velocity changes to the center, then why doesn't the object go to the center? Like, see this guy right here? He's swinging this around. If the velocity is changing to the center, then why doesn't it go to the center? There's a one-word answer. Starts with an I, ends with an Inertia. You know, inertia prevents it from going to the center. Objects want to keep doing what they're doing, you know. Like when the object's right here, which way is it going? It's going that way. So guess what? It wants to keep going that way. But it's not going to go that way because it's being pulled where? It's being pulled to the center. So then it goes, okay, I'm coming. Here I come to the center. Boom, now he's here. Okay, which way is he going there? He's going that way. He wants to keep going that way. But is he going to keep going that way? Because he's being pulled to the center. Total force is always to the center. The reason it doesn't go to the center is because of inertia. All right, now, look. Back when I was a new physics teacher, I thought I was so cool because I would explain like the derivation of this equation, which, to be honest with you, I couldn't do it right now. If you offered me $1 million, could I derive this equation for you? No, because I haven't done it for like 10 years or more. But look, this is the equation for centripetal acceleration. Don't worry about where it comes from. We're just going to use it, okay? This is the equation for centripetal acceleration. V squared over r, where v is the tangential velocity. All right, moving on. Now, centripetal force. Guys, what causes all accelerations? Force. So look, if you have a centripetal acceleration, there must be a centripetal force. And you're all super smart, and you already know that F net equals what? ma. If an object is in a circular path, this net force is going to become centripetal force. If an object is in a circular path, the net force is a centripetal force. Now, I'm going to tell you about a mistake that kids always make. A mistake that kids always make is they go like this. They're like, oh, I get it. So what are the forces you already know? You already know tension. What's tension? Force in a string. Gravity. Friction. Normal force. Centripetal force. Is centripetal force a new force on your list of forces? That's the mistake that kids make or frequently make when they're first doing this. Centripetal force is not, it's not a new force on your list of forces. Don't think of it like that. The way to think about it is like this. The forces that you already know, tension, gravity, friction, normal force, all of those forces can be centripetal forces. Does that make sense? Okay, so like when I swing my keys around like this, ready? Here we go. I'm swinging my keys. What's the centripetal force here? Tension. Tension is the centripetal force. When you're driving your car and you make a turn is just a circular path. What force keeps your car in the circle? Friction. Sometimes you'll have multiple forces as the centripetal force. Sometimes you'll have multiple forces. Like for example, imagine a roller coaster ride going through a loop-de-loop. So here's the roller coaster ride. Woo! Okay, when the car is right there, we freeze it. What are the forces on the car? mg and normal force, which I know some of you are like, whoa, wait a minute, I thought normal force points up. Well, not if the car is upside down under the track, right? Here's the surface right there. Normal force is always perpendicular to the surface. The track is pushing the car down. So what would be the centripetal force here in that diagram? It's those two guys added together. Both of them are the centripetal force, normal force and mg, right? So centripetal force will be the forces that you're already familiar with, okay? So F equals ma. If it's a centripetal force, then your A becomes what? Centripetal. What's the equation for centripetal? V squared over R. So that gives mv squared over R. Is this kind of making sense? So dudes, we're talking about forces here. Let me remind you. How do you do force problems? Step 1, free body diagram. Step 2, sum the forces. Step 3, do the algebra. Look, when you're summing the forces, sum of the forces equals ma. In this chapter, we just have a new a. It's a centripetal acceleration. It's the same basic thing you did in chapter 4. If you hated chapter 4, you're going to hate chapter 7. Although now's your opportunity to love it, you know. What? Chapter 4 was summing forces. So now we're summing forces again, but with centripetal accelerations. All right, so let's try a problem here. Let's do a problem. All right, so we got this car cruising down through a loop-de-loop. I do this all the time, guys. Like right off the 405 freeway, is this real fast. Dude, one time I went through too slow, and if you go through this loop-de-loop too slow, what's going to happen? If you go too slow, you're going to go woo. You're going to crash. Okay. Oh, and by the way, later in this week, I'm going to teach you how to calculate the minimum speed required to not fall out of the loop. Right? We'll talk about that later. There's a minimum speed to not fall out of the loop. So here's the situation. Mass of the car is 700 kilograms. The radius of the loop is 15 meters. And then I give you the velocities at point A, B, and C. I want you to find the normal force at each of those points. You're solving for the normal force at point A, point B, point C, and you have the velocities at those points. Okay? So I'll give you like 10 or 15 minutes. Oh, and here are the answers. I'll give you the answers. At point A, the normal force is 46,107. At point B, the normal force is 25,553. And then at point C, the normal force is 5,086. So you know if you did it right or not. So point A. So the steps you're following, you do free body diagram. So here's the car at point A. What are the forces when the car is at point A? You got mg down. You got normal force up, right? We call it a normal force. Normal means perpendicular to the surface, or normal means perpendicular. So here's the surface right there. The normal force is perpendicular to that. Okay, for circular motion problems, I forgot to mention this earlier, you always make the center of the circle positive when you're summing forces. Now, what's the reason you make the center of the circle positive? What always points to the center? The acceleration. So you want your acceleration positive to keep things simple. I mean, you could not take my advice and make the center of the circle negative, but then that's going to be trickier to deal with. Okay, center of the circle is always positive. So for point A, when you sum the forces, you're going to go normal force up, mg down. Now, what is the sum of the forces going to equal? Now, look, a lot of times students will think like, oh, well, hey, shouldn't these two forces be canceling each other? How many of you, be honest here, how many of you are thinking that? It kind of seems like, well, normal force and mg should be canceling. Nobody? Well, if that were true, if they were canceling, what would the car do? Go in a straight line like that. If the normal force and mg canceled, it'd be going in a straight line. What's the car going to do? A split second after point A, it's going where? Up. So which force has to be bigger? The normal force. The normal force has to be bigger than mg because it's going to travel upward in the circular path. So anyway, the sum of the forces here equals ma, where this a is a what? Centripetal. How did I know it's a centripetal acceleration? Because this car is now in a what? Circular path. Whenever you have a circular path, there's a centripetal acceleration. The equation for centripetal acceleration is v squared over r. Plug that in right there. So now when you solve this for normal force, you're going to get normal force equals mv squared over r plus mg. I would factor out the m just to make it easier. So that's v squared over r plus g. When you plug the numbers in, you get 46,107. Okay? Now, let's skip point B for a minute and go to point C. So going to point C, here's the car, upside down. What are the forces on the car as it passes through point C? You got mg straight down, always straight down, normal force straight down, which I know is weird. It's like, wait a minute, I thought normal force points up. Well, have you guys been on the ride Accelerator at Knott's Berry Farm? Where do you go when you go across, when you hit the top of the loop? Where are you? Underneath it or on top? You're on top. So if you were up here, if you were on top of the loop, then the normal force would point up, right? But are we on top of the loop or underneath it? Underneath it. So what's the track? What's the track doing to the car? So here's the surface. What's the surface doing to the car? Pushing it down. So normal force and mg are both to the center. So when you sum the forces for point C, you're going to get normal force plus mg. Make the center of the circle positive. Okay? Sum of the forces equals ma. That a is a centripetal. So plug in. So the sum of the forces still equals ma, but it's just that the a is a centripetal. So now solve this for normal force. Normal force is going to be mv squared over r minus mg. So factor out the m to make it a little easier. That's going to be v squared over r minus g. So then the normal force is 5,086 at the highest point, at point C. Okay, now back to point B, and then we're done. Now look, point B, it's actually the simplest question. So let me erase this radius here. We're going to draw in the car. So here's the car at point B. What are the forces on the car as it goes through point B? Well, mg straight down. Here's the surface, right? There's the surface right there. So which way is the normal force? To the left. The surface is pushing to the left. Look, are the forces perfectly x? No. Are they perfectly y? No. We have an x force and a y force. So you're going to treat these separately, right? Notice, is mg going to be the centripetal force? Does it point to the center at all? No. It's perpendicular to the center. mg has nothing to do with this problem because it's perpendicular to the direction that points to the center. The center of the circle is right there. What points to the center of the circle? The normal force. So look, when you sum the forces in the x direction for point B, what is the only x force? Normal force. What is that going to equal? So then plug in for centripetal acceleration, you get normal force equals mv squared over r. It's the only force pointing to the center, so it has to be the centripetal force. So when you plug in there, you're going to get 25,553. Okay. Any questions? Yo.
Is the velocity the tangential velocity?
Yeah. These velocities that I gave you are all tangential velocities. Yep.